The modern Earth is a stable, layered world, teeming with life, a sharp departure from its state 4.6 billion years ago. Before it was a planet, Earth existed as part of the solar nebula, a massive, chaotic cloud of cold gas and scattered dust drifting in deep space. Inside that cloud, tiny particles began to collide. Even at this scale, the particles exerted a slight gravitational pull, sticking together to form larger chunks known as planetesimals. Earth emerged through millions of high-speed impacts over eons, gathering mass piece by piece from the spinning debris of the nebula. These constant collisions generated enough heat to turn the young planet into a molten sphere of liquid rock, allowing materials to move freely based on their physical properties. This liquid state initiated density differentiation, a process where elements sorted themselves by weight, much like oil and water. Dense, heavy metals, specifically iron and nickel, sank towards the center of the planet to form the intense, high-pressure inner and outer core. Lighter silicate materials floated to the surface. As these cooled, they solidified into the thick mantle and the thin outer crust. This vertical sorting created the layered anatomy required for a geologically active planet, providing the foundation for our magnetic field and tectonic plates. In its earliest stages, the solar system was a violent environment where the orbits of developing protoplanets frequently intersected. Around 4.4 billion years ago, Earth collided with a planetary body roughly the size of Mars, an event geologists refer to as the Big Splat. The collision blasted a massive ring of vaporized rock and shards of Earth's early crust and mantle into a high-speed orbit around the planet. Over millions of years, this orbiting debris coalesced and cooled to form the Moon. The Moon's gravitational pull began churning the oceans into tides and locked Earth's axial tilt at its current angle, providing the stability for predictable seasons. This planetary catastrophe provided the specific gravitational balance required to stabilize the environment for complex life. Earth's initial primordial atmosphere, composed of hydrogen and helium, was completely stripped away by fierce solar winds in the early solar system. As the planet cooled, extreme pressure forced trapped gases up from the mantle, venting them through the crust in a process called degassing. These volcanic eruptions populated the sky with a new cocktail of water vapor, nitrogen, carbon dioxide, and methane. The early atmosphere was a direct exhalation of the planet's molten interior, rising through the crust as the Earth began to cool. Once temperatures dropped sufficiently, the water vapor in the atmosphere began to condense into liquid rain. Torrential rain fell for centuries, filling the rocky basins of the crust and creating the first primitive oceans. Life emerged in these waters 3.8 billion years ago, eventually evolving the ability to perform photosynthesis. Photosynthesis flooded the atmosphere with oxygen, permanently altering the sky's chemistry to support complex, air-breathing life. The Earth evolved from a violent cloud of dust into a layered, life-sustaining planet, a 4.6 billion-year cycle of geological and atmospheric engineering.